Recursion is the fundamental means of repetition in functional programming languages, but recursion is also supported in nearly all modern programming languages. So this video will first discuss recursion in Java before moving on to examples in functional programming languages. Here we see an example of computing the factorial of n, which results from multiplying together all the numbers from 1 up until n. When done with a loop, an accumulator variable is defined and repeatedly modified here. When done recursively, every call to the recursive function uses a different value of n. Note that I've designated the parameter n as being final, meaning that it cannot be modified. The same is not true of the result variable in the iterative version. The recursive definition has one base case and one recursive case. In the recursive case, the enclosing function is called recursively. Note that the value of n is not changed, but a different value is sent as a parameter in the recursive function call. This main method tests the code and verifies that we get the same answers for both the iterative and recursive versions of the code. But how would such a recursive definition be written in a functional programming language? Lisp is one of the oldest programming languages and the first functional programming language, though the modern language Common Lisp, shown here, has also adopted many features of imperative and object-oriented languages, making it a complicated hybrid. However, I'll mainly be emphasizing functional programming style in this video. Here, we see a factorial function defined using the defun keyword. The n in parentheses is the parameter list. We have an if statement that checks if n is equal to 0. Notice that in Lisp, all functions and operations use prefix notation. If n equals 0, then we go on to the base case and return the value 1. Otherwise, we return the result of the recursive case, which is the result of multiplying n by the result of this recursive call here. Notice that Lisp does not bother with a return keyword. Since we are defining a function, it is assumed we are calculating a result, and that result is automatically returned. In fact, even the if statement here is an example of a function. It is a function that returns either the second parameter or the third parameter, depending on the value of the first parameter. To test this factorial function out, I actually will be using one of Lisp's non-recursive loop constructs right here. If I run this script, I get these values, which are the result of looping from 1 to 10 and printing out the result of each call to my factorial function defined here. However, I don't have to use a looping construct. Everything you can do with loops can be done with recursion. And in fact, here is an example of getting the same output by making a recursive definition. Here I've defined a function called repeat that accepts a current iteration number and a stopping point. As long as current is less than or equal to the stopping point, I will run a little program. And this program consists of first printing the result of factorial with the current numerical value, and then recursively calling repeat again with the first parameter position increased by 1. Now, unusually, this if statement has no third parameter. I simply have a test and then some code that I execute if that test is true. Therefore, the else case defaults to a nil result of nothing. In other words, once we go out of the bounds of the stopping point, we do not execute this code, and because we're making no more recursive calls, this code stops. When I call this code with a starting point of 1 and a stopping point of 10, I'll get the same output as we see here. In many ways, the simplicity of Lisp is to be praised. Nearly everything is a function. All operations use prefix notation uniformly, and although there are some special syntactical features I'm not demonstrating here, for the most part, the only special characters you need to be aware of are parentheses. Of course, when you're using so few special characters, the overabundance of the few that you use can be a bit ugly. There are a lot of parentheses here, and some find reading Lisp code hard to do. A more modern functional programming language with a bit more elegant style is Haskell. Haskell is a strongly typed, purely functional programming language. There are no statically defined types here, but every variable and value must have a type, which Haskell can infer using its type inference engine. However, the types are made as general as possible because Haskell also has good support for polymorphism. Haskell is pure in the sense that it absolutely does not allow for mutable state. In other words, you can't change the values of variables after they've been declared. A consequence of this is that Haskell has no looping constructs. Repetition must be accomplished using recursion. Here is a simple definition of the factorial function. The factorial of n equals the result of 1 if n is equal to 0, or n times factorial of n minus 1 otherwise. This is very similar to the Lisp if statement in that we have a test and then a first result and a second result. If I wanted, I could also spread this definition out across several lines. And some care would be needed because Haskell does use white space to check the syntax of the code. But here is one acceptable way of presenting the same code. Because Haskell has no looping construct, I must come up with a recursive means of testing this function by going through several different values of n. Here is a main function with no parameters. In compiled Haskell code, this is what will be executed. Here I'm defining a function named loop with a current parameter and a stop parameter, much like the repeat function defined in the earlier Lisp code. If current is less than or equal to stop, then I use the special do keyword to execute a series of statements that cause I/O operations. Here I put a string into the console. Show will convert a numeric result to a string result, and here is the result of calling our factorial function using the current value here. I then recursively call loop with current increased by 1 and the same value of stop. Eventually, current will no longer be less than or equal to stop, and I will have to go to the else case, where I return nothing. This is a special result in Haskell that is a type of monad. In fact, all of this I/O done using the do keyword is handled via something called monads, which are a complex mathematical construct that allows Haskell to have I/O and remain functionally pure. This entire function is defined inside of a restricted scope. I cannot execute the loop function from just anywhere. I am letting this loop function be defined within the following code here. And all I do is call loop with a current, meaning starting point, of 1 and a stopping point of 10. I can compile this code and then run it, and we'll get the same factorial output that we've been receiving so far. However, this definition of factorial is not written using typical Haskell style. Haskell supports a powerful feature known as pattern matching that allows us to provide a definition for factorial that looks like this. First, notice that I'm actually defining my new function, pattern match factorial, twice. Haskell checks these in sequence from top to bottom. If it finds that the first parameter is 0, then this pattern will be matched and will simply return a result of 1. Otherwise, n will catch any other parameter, and the result return will be n times the result of this recursive call. If we compare this version of the pattern match with the version we have already, we'll see that they are identical when shown side by side. Here, the plus plus operation concatenates strings, and I'm putting a tab between calls to two distinct versions of our factorial function. I'll compile this and run it, and we get the exact same values side by side. Of course, factorial is a fairly simple recursive function. So what happens when we do something a bit more complex? Let's go back to Java first and analyze a more interesting operation. Here is an iterative definition of the insertion sort algorithm in Java. We'll be sorting an array, and the way we do this is we repeatedly insert the element at index I into the array. And in particular, we're going to insert the element at index I into the portion of the array preceding index I, which we will assume to already be sorted. Here, we have the insert method that takes the value at that index and then loops backwards from j, which starts at index -1, down to 0, as long as the value at that position in the array is greater than the value we're inserting. Notice that we shift values in the array one spot to the right to make room for this value that we're inserting, and then eventually we're able to put our value into that array position. This definition of insertion sort fundamentally depends on mutable state. We have an array, and we modify its contents as we go. We do not return a result, rather we modify the array that was passed in as a parameter. Here we have code testing out this insertion sort algorithm. Here's an initial array that is unsorted. We print out its contents. Then we sort that array and print out the result, which looks like this. Here is the unsorted array, and then the sorted array. So doing insertion sort in a functional programming language, and in general doing it recursively, requires fundamentally rethinking what it means to do insertion sort in terms of non-mutable operations. To define a recursive version of insertion sort in Lisp that uses purely functional style, we will sort a list rather than an array. Now, lists are the primary data structure in Lisp, although Common Lisp does actually support a type of array data structure. We're simply not using it here. Notice that, like everything, we'll be using recursion. We have our insertion sort function, which takes XS, which in this case is a list. We have an if statement that asks, is that list a cons? The cons p function simply checks to see, is the list empty or not? If the list is not empty, then we will execute this code, which is the recursive case. Otherwise, we'll execute this code, which is the base case. In fact, this result here is simply an empty list. In other words, if the list XS is not a cons, meaning it has no elements, then the way you sort an empty list is by returning an empty list. The single quote is used to indicate that we want the value of an empty list rather than a function being executed. In the recursive case, we will insert the first value in the list, known as the car, into the result of calling insertion sort on the remaining values in the list, known as the cdr. Car and cdr are unusually named functions that have to do with the history of Lisp development on an old machine architecture. Later we'll see that in the language Haskell, car is referred to as the head and cdr is referred to as the tail, which are much better names for the first element and the remaining elements of a list. We can now move to the insert function, which takes an element y and inserts it into the list ys in sorted order. The assumption here is that ys is already sorted itself. We first check to see whether y is empty or not. If the list of y's is not empty, then we check to see if our value y is less than the first value in the list of y's. If it is, then it means it's found its place in the list, and we will cons the y to the front of the list of y's. Cons simply means that we put this one element at the front of this list and return the resulting list. Otherwise, we take the car of the list of y's and cons it to the front of this recursive call. You see, y was not less than the first element in the list, so we will instead take that first element and put it before the result of inserting y into what follows. This means we have two base cases. In one base case, we find where y belongs and we put it there. In the other base case, we reach the end of the list, or maybe the list was empty to begin with. If that's the case, we simply make a brand new list consisting of a single element y. This code is tested below. I mentioned before that Lisp allows us to assign variables, and this is an example of that being done using the setQ operation. So this is non-functional style, but it makes the testing easy. We define a list of constants. We know we're defining a list because of the use of this single quote here. This is unsorted. Terpre simply makes a carriage return. We print out the value before, and then we print the values in the list. Then we print a carriage return, print after, and then we print out the result of doing insertion sort on those values. Note that the variable values still contains the original unsorted value of the list. Insertion sort does not change this list. It creates a new list and returns it. That is why we repeatedly cons elements together to construct a brand new list. If I run the code here, we'll see that the before version is unsorted and matches here this value here, and the after version is sorted in order. Perhaps one of the biggest struggles in learning Lisp is the many esoteric function names that don't really make sense in a modern context. CAR stands for Content Address Register because that's where data was stored on a particular machine that Lisp was developed on. But calling the beginning of a list the car and the tail of a list the cdr is quite confusing, and even the word cons takes a bit of getting used to. However, we can create nearly identical code in terms of how it operates in Haskell that looks a bit more elegant and is a bit more readable. Here is code for insertion sort written in Haskell in a way that matches the style of the Lisp code you just saw as closely as possible. We have a list of values referred to as XS. To check if the list is empty, we can use the null function, but we want to make sure that the list is not empty. So if the list is not null, then we have this recursive case. Otherwise, we return an empty list. Notice that this recursive case is very similar to what we saw in Lisp. We insert the head of the list into the result of doing a recursive call, Lisp-style insertion sort, on the tail of the list. The only major difference in the structure of this code is that instead of defining insert as its own function, we're defining it in a local scope. This where keyword is similar to the let in syntax we saw previously, in that it lets us define a function that is only visible within the context of this other function definition. So this insert function cannot be called from anywhere. It can only be called in this block of code here. Otherwise, the insert function is very similar to what we saw in the Lisp code. We're inserting y into the list of y's. If that list is not null, meaning not empty, then we go on to check if y is less than the head of the list. And instead of using a function named cons, Haskell has a special operator. y:(y's) means that we attach the value y to the front of the list y's to create a brand new list, which is of course returned here. Otherwise, we get the head of the list of y's and cons that to the result of making a recursive call where we insert y into the tail of the list of y's. So this is one base case. This is a recursive case. And our second base case comes when the list is empty. If the list is empty, then we are inserting y into an empty list, in which case we simply return a list of that one element. Though completely valid, this version of insertion sort is not the way one would typically write this code in Haskell. And so here is a version using pattern matching, which is more appropriate in Haskell. We have a base case in which we're trying to sort an empty list. Well, sorting an empty list simply returns an empty list. Otherwise, we will pattern match and assume that the list is at least one element, which we'll refer to as x, cons to some other list of elements known as xs. Now note that xs could be an empty list, but we know at this point that there is at least one element in the list. This means that we do not have to explicitly call the head and tail functions. X is the head of the list, and xs is the tail. In this case, we simply insert x into the result of calling insertion sort on the list xs. Note here that this version of insert will refer to the definition here inside of this where clause, which is distinct from the version of insert defined here in this where clause. Each of these two functions has their own local version of the insert function that they rely on. The definition of insert using pattern matching is also different from the Lisp style version. One pattern checks to see if the list parameter is empty, in which case we simply return a list containing the one element y. Otherwise, we know our list must have a head and a tail, which we're referring to as z and z's. We check if y is less than z. If it is, we cons y to the list that results from consing z to the list of z's. Otherwise, we cons z to the result of doing a recursive call to insert, where we insert y into z's. This is a much more compact definition and arguably more elegant. However, both versions behave identically, and we can test them out here. In this code, we will let values equal this list of values, the same we've been using so far, and we will do this sequence of operations, printing before and showing the values before they're sorted, and then for after, we will show both the result of the Lisp style insertion sort and the Haskell style insertion sort. Once again, note that neither of these operations changes values in any way. That is not allowed in Haskell. Instead, we are constructing brand new lists, which are then being displayed to the console. I can compile this code and then run it, and we see the before list and we see two identical after lists. I'll finish with one more example in each of the three languages, the infamous Fibonacci sequence, a sequence that is very easy to define recursively, but notoriously inefficient when done in a naive way. Here is the code for the Fibonacci sequence in Java. We take a value n. If it is 0, we return 0. If it is 1, we return 1. Otherwise, we return the sum of the previous two Fibonacci numbers, fib of n-1 and fib of n-2. The big O time of this code is exponential. It's very inefficient and wasteful because we unnecessarily recompute the same values over and over. Now, there's an obvious way to do this quickly using iteration, but since I'm focusing on recursion, let me show you an O of n approach to compute this result, but still using recursion. This fastFib function calls a helper function defined below with initial values of 0 and 1. The reason that these initial values are chosen is because they are the two base cases, a value of 0 when n is 0 and a value of 1 when n is 1. This is a kickoff for the recursive fastFib helper method. Here we take in n, f0, and f1. Notice that all of these parameters can be final. None of them needs to be changed throughout the computation. If n is 0, then we will return the value of f0. Clearly, if n starts off at 0, it makes sense that we would want to return f0, which equals 0. However, this base case will also work for any value of n. What the recursive case does is it subtracts 1 from n, getting closer to the base case, but it then shifts over f1 into the parameter position where f0 was, and in the parameter position for f1, it computes the sum of f0 and f1. In essence, this code is carrying forward an accumulator as an additional parameter so that that additional parameter can be eventually returned when it is needed when we reach the base case. So it's not completely obvious that this code will return the same value as our simplistic Fibonacci definition, but we can at least test it with a few values here and show that indeed we get the same values for n going from 0 up to 10. Similar recursive definitions can be written in Lisp. First, we have a naive definition of the Fibonacci sequence that is inefficient. It uses the case construct, where we check the value of n. If n is equal to 0, we return 0. If n is equal to 1, we return 1. Those are the two base cases. Otherwise, we compute the sum of fib of n-1 and fib of n-2. But we can also do the efficient fast version of the Fibonacci sequence. Here we have our fastFib function, which is merely a kickoff that calls the fastFib helper, which is the actual recursive function. The parameters are n, 0, and 1. And in our fastFib helper, we have our three parameters. If n is 0, then we return f0. Else, we recursively call fastFib helper, subtract 1 from n, shift f1 into the f0 position, and put the sum of f0 and f1 into the f1 position. This code can be tested here with Common Lisp's loop construct. We'll print out both the naive version and the efficient version with a tab between, and the results are identical to what we saw in Java. Finally, we have examples in Haskell, And these will be written in typical Haskell style using pattern matching. We'll skip over writing Haskell code in Lisp style. The pattern matching version of the naive version of the Fibonacci function simply assigns a result of 0 when the parameter is 0, a result of 1 when the parameter is 1, and the recursive case computes fib of n minus 1 plus fib of n minus 2 whenever n is not one of those two values. For the fast fib function, we will define our helper function within a where clause. We send in n and then 0 and 1 as before. Our base case for when n is 0 returns x. And note that we have an underscore here. This indicates that we don't even care what that second parameter is in this case, which makes sense because y, the second parameter, is not being used in this particular case. It is only being used in the recursive case here. And so since the value of y matters in this case, we give it a name. We recursively call our helper function. We subtract 1 from n. We shift y over into x's position, and we put x plus y in y's former position, and end up computing the same result as before. To test this out, we define a very similar recursive looping function, but now we'll be calling fib and fast fib instead of factorial functions, and we'll loop from 0 to 10. And when this code is run, we once again get the same results as in Lisp and Java. Even without loops and mutable variables, you can compute everything that you would normally compute in a language like Java. It just requires some awareness of more sophisticated types of recursion to be able to do old tricks in a new way.